There it is. All right, thank you. Hello there. Yeah, so you all heard a bit about me. Let's get started with this presentation. A murder of crowds, actors, instrumentation, and load testing as part of the TDD cycle. Sounds like a catchy title. Let's introduce myself a little bit more and the place where I work. I work in Erlang Solutions. You may have heard about us. We are like somewhat one of the maintainers of the very Beam language together with Ericsson. And we work in just what you would expect, the usual distributed, scalable, fault-tolerant system, the Erlang keywords. I'm this person. You can find me everywhere on the internet by this picture, except LinkedIn, because I was told that I need to look professional. So in LinkedIn, I have like a, pro portrait. Otherwise, that's my profile picture everywhere. And these are the two main projects that I work with: MongooseIM, the chat that you heard about, and Amok, the load testing tool that I'm going to mention a little bit today. My career started this day, in a way. And this is like, as was said before by your colleague, when one day I met Robert Virding. This picture is of the actual place and moment when I actually met Robert Virding. This is an original picture. There happened to be a photographer. This was on a meetup here in Krakow. I'm based in Krakow. And I went there as a C developer and curious about Erlang. I have only heard about Erlang like theoretically and read a bit about it, but I had no experience whatsoever. And I went there and I had some questions. I was asking the speaker, the presenter, just like me today. And then at some point, the presenter was like, you know what, I don't know the answer to that, but we can just ask Robert Virding. He's there. My head was like, wait, what? So I went to Robert Virding and I talked to him for hours. That's when I discovered this whole enterprise. And this is where I have been a bit over 5 years. This was, to be precise, in February 2019. So yeah. Anyway, so let's talk a little bit about performance and stuff. All statistic from Google. Google says that if your website takes over 1 second to load, the probability of bounce, that is people that enter and just leave without interacting, increases by this much. If your delay is up to 5 seconds, the probability increases almost totally. It gets worse and worse. Almost 20 years ago, back in the beginning of the internet, Jesus Christ, Amazon found that every 100 milliseconds of latency would cost them 1% in sales. 1% in sales, just put it into numbers, how many billions of dollars that is. Put it into perspective in your business. Like, imagine you would lose 1% of your revenue. It could be a lot of money. Could make a big difference. Another statistic, a broker, for any of you that might be into trading, a broker found that could lose $4 million in revenues per millisecond if their electronic trading platform is 5 milliseconds behind the competition. That is, again, a crazy lot of money per millisecond. This is brutal. Very simple example. Some time ago in January, actually earlier this year, Linus Torvalds posted on the mailing list just a note: I'm bisecting, and I found that this merge has made my merge window miserable. After a certain merge, every time you would merge something else, the whole compilation of the kernel will take way too long. And Linus was like surprisingly polite, to be him this time. You have been warned. This is going to be reverted. Linus Torvalds, 10 of January. A little bit later, 13th of January, this time Saturday, Linus says that there is a winter storm. He's, again, making fun of what they call winter storm, considering that he's coming from Finland. And so he has no connection to the internet. He's not going to be available for merges. And just, winter, just after he announced that, the next day, 14th of January, the person that made the original pull request, the original merge, found out the fix. It's just a one-liner, calculating some statistic, and then that would make the merge very fast. So what if this had happened to a database? Postgres, like the Curiosum guys, you just like had your logo of Postgres there a moment ago. Why is this happen to video game engines? All these gamers investing so much money in the best graphic cards with sub-milliseconds latency and the screen with a refresh rate, and then the engine is lower. Let's talk about performance. What if this could have been prevented? Just a very simple example. Let's go, right? You're ready? Headline of the day, if like you want to remember one thing about this presentation is this: you only care about code you have benchmarked. Like, if you want to ignore me for the rest of the presentation, that is still, I mean, it's not great, but it's still fine. This is the headline, okay? Keeping this in mind, we know, we all have heard of this motto: premature optimization is the root of all evil. But let's not take things out of context. The whole quote says something like this: yet we should not pass up our opportunities in that critical 3%. Far too often we get drowned in improving that 97% of the times when it was useless work, but sometimes, sometimes still, don't lose focus. How do we benchmark? Let's see a few examples. I had a very nice physics teacher in high school. Kudos to him if one day he hears any of my presentations. And I remember when we were studying like Newtonian mechanics and fluids, that he gave this example of this bridge. This bridge was built, if I remember correctly, the Tacoma Narrows, that is in the north west of the US. In a small bay, there is a bridge that was crossing, and during construction, the bridge was already famous for being wobbly. Once construction was finished, it was open really for a very few days. I don't remember how many, until a wind of around 40 miles per hour. I'm a big supporter of the international metric system, but Wikipedia had it in miles per hour. That should be around 60 kilometers per hour. Not a crazy wind. Did that. No casualties except for one dog that was on that car. Now the bridge is a very interesting house for fishes underwater. No, I don't want you to play the video again now. So this happened when we went from bridges that were like this, say I don't know, for those based in Europe, the classic example is your Roman bridge that was made for a Roman legion to cross it. And the bridge was massive and solid. And then we went to bridges like this that are like floating in the air, that their density is way smaller. So likewise, we went from computers that look like this. Back in the days, one of these computers would not fit in my room. And if I punch one of these computers, I would probably just break my hand and nothing else would happen. But now we live in a world of computers like the one I'm giving you a presentation, that if I punch it, I'm afraid my boss would be very sad. So the world has changed, and the same way that we had forces into the bridges that did not make any difference, but now they do, so we do in the internet, in the bridge. I don't want to go into bridges too much, but the old bridge, the Roman bridge, was being crossed by a legion, which is like a couple thousand soldiers with some metal armor. The modern bridge is being crossed by thousands and thousands of cars per minute. And the trucks could be loaded with way heavier stuff. Use it for military exercises. Your military division is like considerably heavier today than it was for the Romans. And the bridge is considerably lighter, spanning way longer distances. So now the force of gravity plays a completely different role. But even so, the force of wind, that the wind in the Roman bridge doesn't make any difference whatsoever. In these modern bridges it does. So does in the internet. So with this analogy of bridges, let's come back to computers. And we say that we only care about code that we have benchmarked, and we need to find the new forces that now make a difference. So I'm going to give a few examples based in MongooseIM. Is the messaging system that I work. on. If you want to have a look, of course, you're more than welcome. Self-promotion inserted, throwable, scalable, and extensible, instant messaging server, written in Erlang. Performance test. Let's start with Benchy. If any of you has not heard about this library, you definitely should try. That's the lowest entry level, super easy to use. It's an Elixir library for micro benchmarking. In my protocol, in my messaging protocol, I have the addresses that are somewhat similar to email addresses. There is only the extra part here that is a resource to distinguish between, for example, like two different phones connected to the same user, when in the email case that doesn't play a difference. And I'm going to try, like, for example, two different implementations to parse this kind of to encode and decode these identifiers. One of them was implemented using a NIF, natively implemented function. The other one is implemented in pure Erlang. And I just generate some random data where like the user, the domain, and the resource are, for example, UUIDs, which is more or less representative. Very often the domain and the name and the resource are going to be UUIDs. Domain is your usual web domain, which might be just as long, more or less. And some examples here, running in the computer and giving you a presentation, latest and greatest Apple Mac, and I'm very proud of this computer. Found out that the Erlang code is around 2 times faster, the pure Erlang. Nice. Of course, this is running in Erlang 26 with the JIT compiler. This was not true back in the days of Erlang 22 when the NIF was implemented. But, it's a very simple encoding and decoding algorithm. There is no grandiose magic. So, yeah, it's easy. Anyway, a bit more complicated. My messaging server is based in XML as the markup language, as the transport language. And so a very hot part of the code is encoded and decoding XML. If I go for the standard Erlang library, this EXML scan, and then compare it with a custom implementation that we had, which is again using the NIFs, and I parse against like different sizes of messages, and then I run this benchmark. I get something more or less like this. This time, I guess no surprise, the C code is going to be a lot faster. This how much is a lot faster depends on the size of the input. There is a funny effect here where more or less it's like 30, 30, 20, suddenly 5, and then again 20 times lower. What the hell happened here? This is the size of the cache in my computer. So at this point, cache misses makes a difference until the package is so big that the cache miss doesn't make a difference anymore. And then you recover. But it's an interesting point that could tell you a lot about the optimizations that you can run. For example, if you're going to deploy in a server that has this much memory, or this being a messaging server, like 37 kilobytes, that is like, how to compare? The Book of Revelations, the Apocalypse, is around 50 kilobytes. So more or less, this is like almost as big as the Book of Revelation. Who writes that? Like, when my grandma writes to the family chat, she doesn't write that much. So that's probably not the case I need to optimize for a messaging server. This was done with Benchy. You should all be familiar with it. Now, this was a micro benchmarking. What about load test? Now let's do something else. Let's say that I'm going to build some specs for 2 different users. So, the username, the password, whatever they need to be configured. And in a loop, I'm going to have them send a message to each other. So Alice sends a message to Bob, and Bob receives and verifies that it is such a message. And send one of these messages every 10 seconds. Let's use an example. This is something that I could do. I could run one of these, and then I could run an infinite number of these and see how my server behaves when the number of pairs of people connecting, texting to each other increases. So in our server, this is running like 1 load testing master node and 2 load testing worker nodes, 2 MongooseIM with Postgres. This is the scenario, 100,000 users. Here you have the names of the machines for AWS if you want to have a look. Users connect every 5 milliseconds, and every 10 they send a message 60 times. Results are something like this into different configurations. The median is around 3-4 milliseconds. The 95 percentiles is around 16-18 milliseconds. The difference in the configuration is not part of the presentation. This is done with Amok, a load testing framework for running massively parallel tests. Now, you might be already familiar with Erlang and Elixir, so you might be guessing how this is going to work. Just, one process is one scenario, and you can spawn an infinite number of them. So stress test is something that I'm not going to give you many examples for a lack of time. Stress test is how what happens when your server dies, when you test it up to a point when the server dies. You want to test how it dies, basically. And this is something that we programmers have the luxury to be able to do, and you should not forget about that. Compare with bridge builders. The guy building a bridge does not have the chance to see what happens when you overload the bridge and it falls. It's, first of all, way too expensive. Also an ecological disaster. It's also like it takes way too much time. It's impossible. It's out of the question. But we can just duplicate the server. We can just replicate a copy. It costs some money because load hardware. But please, we are very privileged. So 3 kinds of tests: performance at minimum load. Bench is a library that I recommend you a lot for that. And then load to see how the system scales, and stress to see how the system fails. For this, I would recommend Amok, our load testing tool. Let's see a little bit more details about this. We're getting more into the topic, test-driven development. So I want to argue that when you are offering a service, imagine I'm offering you this messaging system, and it is correct. Alice sends a message, Bob receives, the whole routing, formatting, everything is fantastic. But imagine that this message takes 10 seconds to be delivered. Is this a real-time messaging system? Obviously not. And I want to argue that the time operation takes are part of the specification. And in test-driven development, what you do is that you test the specification beforehand. Step by step, you build a test that verifies a part of the specification, and then you implement that specification and then iterate. But at the end of the day, your tests are like a definition of the specification, the usual TDD with when, if, then, etc., etc. It's describing. And so time performance is part of the specification. So I also want to have it tested that is correct. So let's write a test. So get the usual, this is in Erlang, common test. I'm using Scalus. Scalus is a helper library for the client XMPP. And I create with this helper first story to users. And then I have Bob create a stanza and send it to Alice. Sorry, the other way around. Alice sends a stanza to Bob. Bob waits for it and verifies that it's correct. And vice versa, exactly the same thing, but symmetric. And this is wrapped into a story that creates a fresh Alice and Bob, so I can run these things in parallel without interference, and executes it, and I get results something like this. It fails, TDD, so you make it pass, you write your source code, voila, it's green, fantastic. Now, refactor and repeat. Now, very important here is that this test took 0.075 seconds. That is 75 milliseconds. This is the time it took in my test to create 2 completely new users, have them establish a connection, message each other, verify that the message is correct when delivered, and then close the connection. All that other extra logic is handled inside of the Scalus story. That's a helper anyway. So this is how long it takes. Imagine that this test had been green, but in 3 seconds. Is this like what I want to offer? Also, CI takes way too long to, if every test takes 3 seconds, oh God. So let's have a look at this. Let's take away from measurements all the parts about creating a connection, creating the user, establishing a connection, and so on. Let's test only the delivery. So again, using Benchy, micro benchmarking, I'm going to say before each scenario, generate 2 new clients and have them connected and so on, run the scenario, and then after each, close the connection. So this time the measurements do not take into account all the other stuff. So this time, this is like the transliteration to Elixir of the same thing you saw before, so no surprises. As I say before, wrapped that scenario, exactly the same than before, have them writing a message to each other, receiving them, verifying, then close the connections. This take, in my computer, in the average, way below 1 millisecond, the 99th percentile around 1.5 milliseconds. I'm happy about this result. I can sell this messaging system. But then, what if one day I make a change of code and this gets worse? I will need to know about that. So let's first of all try to run this in parallel a little bit and run the test for also a bit longer. And same thing than before, I'm going to just give you some examples. When I'm running one Alice and Bob sending a message to each other, this is how long it takes, as you saw before. But when I'm writing 12, number of course my computer has, gets worse. But then when I say, like when I multiply the parallelism more and more, it doesn't get much worse. It remains pretty stable up to the parallelism that my computer can have. So yeah, that's fine. It gets worse, but it's still like a very good number. And then increasing the concurrency doesn't make it much worse. So good. Now I have an idea of the micro performance of my program. So I'm going to define the specification. I want to know that I want to have tests for the specification, as I just said before. So there are different lines where I can design this specification. One is, for example, with SLAs, message delivery within. We are going to deal with noise, but first of all, there is a common myth of delivery has to happen within 200 milliseconds. That's the SLA. What if it's 201? What if it's almost always 199 and then one day is 201? What about all messages are being equal? There might be bigger messages or more chatty users. So what about defining an SLA considering statistics? So the mean is going to be this much, and then you're going to establish, the percentiles and the maximums instead of a hard line. The maximum is 200 milliseconds. 200 milliseconds is still not that fast. But if you want to define 5 milliseconds, that's quite fast, especially if you start putting extra processing, if you put like extra customizations, things that happen per message, like, I don't know, push notifications, for example. So very similar, I'm doing messaging, but many of you might be doing web. So HTTP first content delivery. Another idea, another notion to define is latency versus throughput. That is time per action or actions per time of unit. Might depend on your use case. You're going to prefer one or the other. And expected behavior at failure, full blackouts, the whole thing dies. Partial blackouts, that is, I cut the service to part of my customers, but to some others, they continue working exactly as it was. Or a brownout, that this comes from electrical terminology when there is a over demand of electricity providers use like lower the voltage. So some of your hardware may malfunction because there is not enough power, but I don't know, the light bulb is still going to be on. But this is to be considered as part of your product decision because, for example, in the case of electricity, you cannot do a burnout to a hospital. That's out of the question. It's impossible. You cannot do that. So you need to, take this decision as a product decision. What is it, the specification, and then test for it. So how to measure these things? I gave you some measurements before that were wall clock, but wall clock has limitations. First of all, a very funny edge case that never hits until it hits and then everything is a mess is time warps. Clocks are not exact, and every once in a while they are resynchronizing. clock, my computer has a crystal course that has a fantastic measurement of time, but every few weeks it gets a millisecond off and it gets told from the internet, hey, just delay your clock a millisecond. And then my measurement can be 1 millisecond ahead or behind. And you will never know about this. It is very hard to correlate. A bit more crazy when you get summertime savings, and then your computer clock just jumps by an hour, and just by coincidence at that time you were measuring something and your measurement is off by an hour. You will probably notice that's like very screamy, but a millisecond you may not notice. Another problem is expensive and it gets a lot of noise. So that works. Expensive. It requires memory barriers. When you have modern processors, the clock is a global counter, so you need to put memory barriers. It's expensive to compute when it comes to parallelism. And it is influenced by voltage. As I say, imagine that your electrical provider has a very minute brownout, and this tiny 0.001% of voltage change makes your clock delayed by a millisecond a year. But if you are testing something exactly at that moment, so we are going to better use counters. You need to know yours. CPUs have performance counters. Databases have their own. For CPUs, do we need to introduce perf? I hope that this is even more well known than Chi for most of you. Database counters, they also have their own, and interpreting counters. Your language, in this case, we're talking about Erlang, Elixir, Gleam, you name it. The Beam has performance counters, reductions. You have all heard about those. I'm going to also break a little myth. Sometimes I also introduce these topics to people from other languages, and then some people say, yeah, no, but I program in C and it doesn't have... C is an interpreted language. There is no language that is not interpreted. It's a myth. Processors, since I believe Pentium 2 or 3, I'm not sure now, Intel x86, they wanted to introduce some performance in the hardware that would break backwards compatibility. So what they created in the hardware was a virtual machine. And your super fancy compile assembly code is interpreted at real time by the hardware. That's how you get CPU fixes. When there is a CPU bug and then you download some microcode, it's software built into the hardware. So even C is interpreted and the processor has counters for that. Of course, it's a different layer of interpretation. So yeah, okay. But being purist. So dealing with noise. This is the trickiest part here. What are we doing with time? Perfect. We're going to define performance in terms of throughput, latency, or memory. And we have one problem. We were saying before, for example, DSLA, my message delivery is going to be 200 milliseconds. That's quite a lot, right? Considering like from the moment the message enters my servers to the moment it leaves, then maybe between my server and the client can be problems. I don't know, his network can be shitty and then takes longer. But within my server processing, 200 milliseconds is not that fast. I mean, human-wise, it's pretty instant, but so what am I going to say? 10? That's maybe, what if it's sometime 9? Then it's 10, then it's 9. What about noise? First of all, it's manual work. For every part of the implementation, you need to think about how much time it should take and decide. And this may not scale well with the number of things you need to decide what is a reasonable time. The very big problem is the background variance. Computers can have some noise. Maybe exactly when I was testing using CI on GitHub Actions, for example, this is run on a hardware that is shared, and there were more processes running there. So context switching in the processor and everything got a millisecond delayed, and I broke my SLA. And again, this measurement doesn't know of the context that is running in these circumstances. So the challenge is that I need automatically applied thresholds that are resilient against noise variance and are context aware. Another point about context awareness can be, I have my code that I say my SLA is 200 milliseconds and my measurement right now is 100, but I make some code, it grows. At some point it's 190. but it's still green. My tests are green, everything is fine. And then one day I just changed some documentation, but because of noise or because of, I don't know, together with the documentation, there was a change of the building pipeline, God knows what, and then a little bit of noise, and that 190 something jumps over the threshold, and my change of documentations says that fails in CI. So we are going to deal with this using a little statistical trick. I studied mathematics, as it was mentioned before, not programming. And I'm going to be honest, statistics was one of those subjects that I hated back in college, and I was avoiding it like with my life. But in retrospect, I regret it. I think it was a lot more useful than I thought it would be. So let me show you a little trick that I still managed to remember. Nevertheless, I mean, I studied mathematics, so if like 10 years later I need to come back to this, I have a certain understanding on the background, so I can, but you know, I should have been a better student. Anyway, so we have two distributions. My distributions here are normal. That means that the tails are small and the center is bigger. And in this distribution, you have the concept of the average. The blue and the red ones have the same average, but you can see that the population is completely different. My hypothesis is that your performance measurements are going to have a distribution like the red one. They are going to tend to be very clustered. Like if a test says that this takes 7 milliseconds, it's almost always going to take something very close to 7 milliseconds. It's not sometimes going to take 700 and then 0, and then my average is 7. That would be a really weird test and performance. That's something is extremely flashy if you get a really high variance. So variance should be very small. And there is this little trick. Measure the variance. The variance is a mathematical formula. It's the square root of the squares of the sums of the elements of the population. Just find your formula. This rule says that on the average, one standard deviation to the left and to the right contains 68% of the population. 68% of the measurements are going to be this far away from the average. And 95% of the measurements are going to be this much far away from the average. That is 2 standard deviations. The standard deviation is the square root of the average. It's the square root of, find the formula. And 99.7% of the measurements, which is almost all of them, are going to be 3 standard deviations away from the average. So this is how far my measurement should be. So this is something that I could use as a threshold. If I have data from the last 100 runs, 100M, I define that anomaly as like given the test number 101, it is anormal if the result of that is more than 3 times away from the standard deviation. And this is when test should say, well, something's flashy here. And then you could investigate, like maybe it got away from the standard deviation, but lower, but maybe it was part of what you were testing, what you were implementing. You wanted to make something faster. So your test should say red flag here, and then you should say, yeah, this is good. Use this to calculate the future averages. This you also need to measure for the coefficient of variance, this CV. I would argue that 0.1 is a decent value. This is standard deviation divided by the mean, not the average. And coefficient of variance would help you against the case when, if you're tracking the last M runs, like if you're tracking all of them, you have the real average. But if you're tracking only the last 100, what if every test it's getting like 1 nanosecond slower? After 1 million runs, you know, 1 million nanoseconds, that's already a second slower. It's growing up, but in the last 100, the average and the measurements is everything is within the narrow band. So it's green. So you want to also test for the coefficient of variance, which is a measurement of how much the variance jumps away. An idea, like you have a red or a blue distribution, basically. And when you run a test, you could run the test several times and take the best value. What do I mean with this? If I run my previous Benchy test and I say that the measurement is, sometimes I get 2 milliseconds, sometimes 3, sometimes 2.5, sometimes 2.7. Common practice is to take the average of a bunch of measurements, because you know that measurements will have noise, so you would measure more than once and then take the average. The problem is that you're taking the average of the noise. When you take the best result means the result with less possible noise. So you don't take the average of end runs, you do end runs and take the best, and that is your final result for this test. So this would look something like this. Here you have your average. This is 1 standard deviation. This is your 3 standard deviations. And my test runs are going to be like this. And one day there is a test that goes outside of my 3 standard deviations. CI complains and I manually check if that is expected or not. Now, this idea of manually check is something that what we wanted to avoid to begin with. It would happen only if wait, I was just having a look at time. It would happen only if either you change something that got your performance worse, and then you should be told, or you change something that got your performance better, and hopefully it was intentional, and then you are told, yes, your performance improvement is a performance improvement. Or even stranger, if it gets better and you have no idea why, then yeah, this is very good news, but still you should really investigate why it got better. Don't let it just pass and say, yeah, so cool. So last point, know your tool. I'm going to spark a little bit of competition. When it comes to load testing, the market is a bit wider. When it comes to micro benchmarking, I think that your solution, if you're not familiar with this, you're running Elixir, use Benchy, is perfect. Maybe there is some other solution, but it's just fantastic. But when it comes to load testing, the market is not that clear. There is a few tools, let me come back to this, that are somewhat popular. An old classic is JMeter. That's it's very well incorporated into the Java world, so Java people would usually default to that. But outside of that, JMeter has some problems of scalability. There is Gatling, which is in Scala, so again, the Java ecosystem may default to that. Gatling is a little bit better. So there is one tool that I believe is very nice for all, being fair. This tool is amazing. It's called K6 from Grafana. It's implemented in Go, and you write your scenario in JavaScript, and has very good integrations. And they run some, performance testing of the performance tool and a comparison with all the other open standard, as I mentioned before, Gatling, JMeter, Zoom, etc. And in general, the only one that was relatively competitive to K6 was Gatling, according to K6 results. All the others, when it comes to performance, they get so much worse. So I got curious about this, and I had a chance to talk about this with people from the Grafana team. So I'm going to say that I'm not attacking them gratuitously. It's a fantastic tool, but there is one little thing where I want them, and I'm very proud about this one. An example, I have a server that is just a echo server, and I'm going to spawn 12,000 connections as fast as possible, have them connected, send 100, how many did I say here? Yes, 100 loop 100 times, generate some random binary UUID, send it and wait for the echo, and then finish the test. And very similar, I wrote the same idea in Amok, my load testing tool, where I just start some telemetry handlers to gather some metrics, and then likewise, I'm going to start a TCP connection, loop 100 times, generate a UUID, send it, and wait for the answer, and verify that the answer is the same, and close the connection. And on average, this was around 15 times faster in Amok. While K6 has amazing integration with Grafana, for example, which is I'm jealous as hell about that. And also K6 has very good usability, the configuration, how you create the scenario is very friendly. When you're running load test, you want to see if your website can resist Christmas, when your e-commerce website selling like Christmas socks is going to handle the demand a week before Christmas. There is going to be 10 million people buying your socks, and you want to see if your website, you need to simulate 10 million clients. To simulate 10 million clients, you're going to need a lot of hardware, and that hardware costs money. So if you need 15 times less hardware, you're going to save a lot of money running your verification. Similar idea in a bit more useful case. This time is a web server that is just serving static pages and it's not looping. Looping made a bit of a different. Same concept. This time I wrote my scenario in Elixir. Amok is written in Erlang, but you can write your scenarios in Elixir. I'm pending to try Gleam. I believe it's possible, but I haven't proven it. So give me a couple of weeks. So this time I'm using in Elixir this amazing library called Reg. If you're not familiar with it, it's your best HTTP client for Elixir. It's amazing. So I'm using that, checking the websites, and this time it's around 5 times faster. So still like 5 times less hardware when you're running something big. The difference between one Raspberry Pi and 5 Raspberry Pis, nobody cares. But the difference between one data center and 5 data centers, holy crap, that's like, you want to save that. So things you would want to run in your load test, please check the documentation from Amok on this. With Amok, you have facilities to throttle and coordinate. So you can like arrange sets of clients. For example, you want to verify that a set of clients are buying the same item and some of them will run out of it. So you can coordinate as you are running your clients that they would coordinate with each other and try to buy at the same time and see about the answers of each other. It's just an example. I'm finishing quickly. And likewise with throttle, if you want to test connections and running the test, then you need to gather data to know how the test was run. And now another like important remark: instrumentation is not metrics. It's not the same. If anybody of you has heard about telemetry, very popular in the Elixir ecosystem as well in the Erlang one. Telemetry is a library for instrumentation, not for metrics. Instrumentation is about enabling visibility, and metrics is about gathering data that visibility produces and constructing that data in a useful way, your metrics. So perf, for example, that I mentioned before, if you want to profile and see what you need to improve, perf is a front end. It's just a collection gatherer to kernel traces and probes. The perf is just telling to the kernel, hey, can you just please insert here some extra assembly code, gather some metrics, do this, do that, give me all the results, and then perf just writes, produces the reports. So instrumentation is when it matters, hey, screen this thing, and let the listener pick up. This is the logic that we enable in Amok. So you can integrate your own handlers to gather the data of your test and integrate that data with CI, which is what I just talked about extensively before, and I think is one of my favorite points about this presentation. Amok enables you to gather the data and transform it in a useful way as CI would use it. This is an idea of how this is a snippet of how this is implemented in Amok. You basically provide this start callback, which is like a single client, and this is run inside of a telemetry span. So everything your telemetry span has, this would have it. And I get a bunch of other handlers. If you're familiar with Elixir, this should be familiar to you. And to end, I want to end with a quote from our beloved Joe Armstrong. I hope that many of you would be familiar with him, creator of Erlang. First, make it work. Second, make it beautiful. Third, if you really, really have to, make it fast, but have it measured first. Right? That's all from me. Questions? Thank you very much. Here.
Yeah, thank you for your presentation. It's been a really interesting journey through both the business end of all the aspects of load and stress testing. There's plenty of quotes that are going to be remembered by us after this presentation. I'm sure many of this information you gave us is going to leave us, thinking for quite a long time about how to improve our load testing procedures, and that's highly appreciated that you brought us to us. And now I think we are going to open our Q&A session. Just let me pick the right button on the left hand side, or actually at the bottom of the screen. I never seem to remember where it actually is. Just let me look it up. Okay, it's now turned on. Yeah. So you can write your questions in the chat in the questions tab in order to ask them to Nelson.
Yeah, I see already in the chat, while people write, I see already in the chat there was one question asked just a couple of minutes ago by Alex. Should we start testing an Erlang cluster from start, not one node? What process registry would you recommend? Testing an Erlang cluster from the start, yes. There is this common practice when you run deployments to always deploy 3 nodes. And because, one dies, the other picks up. Why 3 and not 2? Because if one dies, the other 2, the remaining node may have to pick up more load than it can handle. So if one node dies and is at 100%, the other node is going to be way over its 100 and is going to die as well. So on the other hand, if you run too many nodes, it's expensive. So you don't want to run like 100 just to have like super amazing fault tolerance, because they're expensive. But 3 gets you a usual good sweet point. That considered, then yes, run your test against 3 nodes and test again. It's a very common case when you have a distributed application in the cluster, that there is part of the logic that might be local to one node or another, and there is a certain behavior pattern. There is now in the Q&A, perfect. There are certain behavior patterns of your program you might not have caught that trigger very asymmetrical load. So even though your users are symmetric to your 3 nodes, one of them is going to be way more overloaded than the other because of something in your architecture. So you may want to catch that from the beginning. If you're testing against one node, you are like effectively not testing if your distribution of work is symmetric between the nodes. Process registry, what process registry would I recommend? If you don't know what you're doing, PG, the standard one from OTP, that is like the how to call it, the Swiss Army process registry. And then there are specialized cases. There is one, I never remember the name, SCG or something like that, SCP, that has like some more specific use cases. If you know why you need it, then use it. But as a rule of thumb, if you don't know why using a different one, don't use a different one. That's usually I like to keep things simple. Also, for a completely unrelated reason to load testing, when you need to hire a new engineer, they will need to be onboarded. So, question from Discord. We have another question.
This benchmark testing needs to be done on an architecture similar to production, is that correct? And if so, how do you arrange that? Building a shadow of prod can be quite expensive. Thank you for the great presentation.
Thanks. Performance counters. Benchi gives you some facilities for that, for example, and I'm working a little bit on giving you some like out-of-the-box facility for that in Amok to count reductions. And given an algorithm, the number of reductions in the Erlang VM are going to be the same whether you run this on a massive ARM 128 cores versus like maybe a Raspberry Pi. Is a very extreme example, but the number of reduction is going to be the same even if it took longer to execute. So if you want like testing in CI that gets like not dependent to architecture, count reductions. This is what you would usually count, as I said before, your language, your framework, what's the word for this? Runtime, your runtime counters. Like all languages, pretty much all runtimes offer you counters. Even super low level C, you have CPU counters instead of wall clock. And Perf even will give you statistics about cache misses, things like that, that tend to be, well, the cache miss is architecture dependent because it depends on the size of the cache. But pipeline stalls, for example, is not architecture dependent. Pipeline stalls, if you are into low level, that is when there is a conditional and the CPU starts executing one branch of the conditional, but then it needs to drop that because the conditional resulted to the other. And then the pipeline, the CPU is processing things in a pipeline, it's stalled. That is a stall. That would not be architecture dependent, and the CPU gives you counters for that.
Thank you for your answer. And we have a brief follow-up on the previous one from Paulo Renato. Another one is Process Hub. It pertains to the process registry thing, I think.
I'm going to Google this one. I don't remember. I may have heard, but I forgot. So looking it up. Thank you.
Yeah, thank you anyway for this follow-up. So we are waiting for a few more questions from the audience. If someone is interested in hearing an answer to anything from Nelson, then I guess this is the right time to do so.
In the meantime, I'm going to take the time to like small digression. I see in the list of attendees a bunch of seemingly Hispanic names, and I just want to like say hello, completely off topic. I'm Venezuelan, so hey, nice to see you.
Yeah, I used to learn just a little bit of Spanish, but probably not enough to to hold a smooth conversation right now. So I am not going to switch the language myself.
No, don't worry. I would struggle about computers in Spanish. Like every second word is in English. It's like so hard. So yeah.
Yeah, it's interesting. Yeah, I think I talked to you just briefly before before we started that the time zone is probably quite good for a number of people from the Americas. So
Close to my.
good. I see there's not really anything else coming up in the questions. We can wait for a moment more. I think we still have just a little bit of time for that. But if there is no interest in further questions, then we'll be.
I have a question for the public. Feel free to write it here or just ping me on Twitter, LinkedIn, you name it. Find me on the web. What load testing tools do you use? What performance tools do you use? What experience do you have with like production? And I would love to like know more about use cases. So as I said, with the Amok tool, that is a small side project that we have in our team that I'm very proud of, especially in comparison to Grafana K6. This is recorded. Somebody is going to bite me for this one day. But, Grafana K6 is a big team with a lot of funding. Amok is like me on my free time and we have better performance. So I'm like super happy about this. But anyway.
Yeah, I guess it would be a good time to share that also on our Discord if you would like to join our server to discuss with the participants of the meetup afterwards. I think it's going to be a great idea to continue this there. So we have the link here in the chat, I guess. And now, since I don't see, okay, I see a question from Konrad. So here it is. I'm going to show it up just now. I have a question about limits. How small can we make the minimum delay, and can we achieve 0 milliseconds? And if so, when can we achieve this?
You mean in the example of message delivery, how close can we get to 0?
Yeah, I think that would be the implication of this kind of question. So basically, an absolute 0 is something we can never really see in practice. But it's purely theoretical. But I guess there are techniques that can bring us a bit closer to that figure.
This is the other side of performance work. It's a usual feedback loop where you establish. I wanted to talk today about integrating this into your CI and having, this safety net that tells you performance as part of your specification is getting red or green. But there is the other side of working performance, which is something that I do a lot. And it's the feedback loop between measurement and profiling. So I think that how small can we make the minimum delay? That really depends on your program. Like, there are like use cases, maybe you have like customizations, things, etc. But given a program with a specification and it has a number, now let's work on making that number smaller. Maybe we are happy, let's say 5 milliseconds, awesome. But what if we want it to be 1? Now we need to work on this. We have the measurement. Now we would need to measure what is being executed during those 5 milliseconds. Can we shave off a millisecond here, another one there, we go to 3, then etc. And to find this information, that's profiling. And you have like 2 levels of profiling. One is usually integrated into your language framework. In the case of Erlang and Elixir, we have cprof, mprof, tprof, fprof. There is like a bunch of them. There is 2 of them that are being deprecated in favor of tprof in the latest OTP 27, but nevertheless, have a look at the documentation. OTP has plenty. There is a page on performance that has plenty of documentations on tools for profiling, for testing lock contention, for example. That could be a case with like some hot ETS table, and then this one scale after 64 cores, things like that. There are plenty of tools in the framework that will tell you where is the waiting, where is what function took how long. fprof, for example, is super detailed in the Erlang level, in the Beam level, but it's also a bit expensive to compute. fprof will tell you how long a function took and how long the functions that function is calling take. So then you know if the time is spent on your function or inside in the other stuff this function is calling, and you can draw call stacks. Flame graphs will give you also a lot of visual data about what functions are taking longer. Sometimes you also want to know about what part of the code maybe is fast, it's not taking long, but it's the most often called. So it's very hot. So something that is 50 nanoseconds and you make it 45 nanoseconds, but this is called millions of times per second, this accumulates. So these are the usual 2 points. Find hot code, which might already be fast, but you wanted to make it even faster because it's very hot. Or find code that happens sufficiently often. Like if you have something that maybe is not too fast, but it's called, I don't know, once, I don't know, a night job. At night, there is a timeout at midnight, run this cleanup, and it takes 3 seconds. Don't optimize it, like manpower costs money. Lower in profiling, perf. But perf is on the Linux world. If you're working on BSD, you would use different tools. The idea is the same. At the end of the day, your code is being executed on a hardware and is being orchestrated by a kernel. So the kernel has privileges on the hardware. So there are programs like perf that will tell the kernel, hey, use your privileges to see inside of the assembly that this program is executing. And your kernel integrated with the hardware can tell you statistics about likewise functions, CPUs, stalls. Very interesting since the JIT compiler in OTP, so 24 for x86 and OTP 25 for ARM architectures, you can use perf to draw Erlang call stacks. So in the past, perf would tell you the C call stack of the beam, but that may not tell you how your Erlang code is running nevertheless. Now it does. So read the documentation. Perf is quite a dragon to use, but it's a very powerful tool. And it's like the best at some point. The moment when you can see Erlang calls in perf is amazing.
All right, thank you for your answer. We don't have any more questions right now. So if there is no further question in about, let's say, 30 seconds or maybe 1 minute, then we'll be urging to a conclusion of this talk. So overall, as I said, this is a very interesting topic that we would like to have covered in the future in our meetups. I guess this presentation by Nelson should be like a signal to people interested in giving talks during the meetups to also try touching on the topic and providing some insights on it. And it's going to be a great one for us and for the community as well. So I think since there are no more questions right now, thank you again, Nelson, for your awesome presentation. It's really been an honor to have you there. And as a conclusion of this meetup, let's move on very briefly to the next one. And then in the next meetup, Paolo Renato, who is here with us today, is going to speak to us about Elixir scribe tool, clean code in a clean software architecture. So that's a very interesting one, and surely a reason to stay tuned to the next edition of this meetup in a month. So feel invited to register to the next meetup using the button at the top, or just head on over to curiosum.com to get more information on the next one. So thank you very much, Nelson, for your awesome presentation again. This is the conclusion and the finish of today's meetup. Thank you very much, everyone, for being with us today. It's a really great that we always have plenty of Elixir lovers with us. And the last thing I would like to ask you guys to do is to fill in a quick survey about today's speaker and today's meetup. So I'm showing the survey right now, and you have a chance to fill it in to pass some feedback to us as the organizers and also to Nelson as the speaker. So thank you very much again, and see you next month.
Thank you very much.